Alright, so let's talk about enantiomers and diastereomers. These are two of the more commonly observed stereoisomers that you're going to see where we have stereocenters. So previously you've seen stereoisomers labeled cis and trans, but that is pretty specific. That's only for alkenes and cycloalkanes. When we have compounds that have at least one carbon atom with a stereocenter, in other words 4 different groups around it, we can represent by a star. Because in the case of this molecule there are 2 different ways to represent how we can arrange those groups, then these 2 representations could either be exactly the same thing, or they could be they could have opposite stereochemistries. So what I want to do here is to show you how can we tell if these 2 mirror images, notice how these 2 compounds look to be mirror images of each other, if this dotted line represents a mirror plane. These 2 things look very similar. These are mirror images, but it turns out that if you take this compound and flip it on its back and try to fit it over here, you would have the OH and the CH3CH2 match up because they're all on the plane of the board, but when you turn this over, the hydrogen and the methyl wouldn't match. That makes these enantiomers, they're non-superimposable mirror images. Now one other way to actually check that is by looking at the configuration about each stereocenter, in other words if it's R or S. So let's just assign some priorities here. Each of the groups on each carbon is exactly the same, so I'm going to put the same priorities on each one. Hydrogen, of course, has the lowest priority because it's the smallest, has the smallest atomic mass. Oxygen has the highest priority because it has the highest atomic mass. The ethyl group here has carbon connected to carbon. This guy here has carbon connected to hydrogen, therefore this ethyl group has higher priority, and so therefore the methyl is left with priority number 3. And then once we've done this, our lowest priority group in each case is already pointing away from us, so we just see when we go 1, 2, 3, do we go clockwise or counterclockwise? In this way you can see we're going counterclockwise. We're going opposite to the way that you would normally see on a clock, so therefore that is S. Here, can you see that we go clockwise, so this is R. So whenever you have 2 mirror images like this, with 1 stereocenter, check to see what the stereochemistry is of each. If both of these ended up being R, then these 2 representations would be of an identical compound. Opposite stereocenters means they are enantiomers. They're non-superimposable mirror images. Let's have another example of that. Enantiomers are identical. Take a look at these 2 compounds. Notice how there's a bromine, a CH3, a hydrogen, and a CH2OH. Exactly the same groups around the stereocenter, the chiral carbon. But do these 2 representations represent the same molecule, or are they enantiomers? Well, I'm sure you can see it's kind of hard to tell from this vantage point, but there's something that you can do. Notice how in each case the CH2OH is in the same position. It's pointing straight up in the plane of the board. So what we can actually do is rotate around this bond and move the locations of these 3 so we can try and get all 3 groups in exactly the same position. So what we're going to try and do is rotate this around this bond to try and get the bromine over here so it's opposite to where it is over here. So what I'm going to do is I'm going to draw out this stereocenter exactly the same way that it was. Because we're grabbing hold of the CH2OH and rotating around it, that is going to stay where it was originally. We're going to rotate around this way to get the bromine over here in the plane of the board, and if we do that, notice that with regards to the CH2OH and the bromine, you have a mirror image so far. So if we've rotated those, the bromine was over here, obviously the bromine can't be on the wedge anymore. The methyl group cannot be on the dash because all our groups will have moved. And if it can't be on the dash, the only other place it can be is on the wedge. And then the hydrogen, of course, can't be where it was originally. So when you look at these 2 compounds, can you see that everything looks to be in a mirror image relationship? The methyl is on the wedge in each case, the hydrogen is on the dash in each case, and the bromine is in the plane of the board. Therefore, this and this are mirror images of each other, which makes these two enantiomers. Right? If you would try to take this compound and flip it on its back and put the bromine here and the CH2OH here, you'd see that CH3 and the H don't fit. Therefore, that's why these are enantiomers. But if you want to check to be sure if indeed they are enantiomers, these should have opposite stereochemistries. So let's do our priorities again. Hydrogen's got the lowest priority, bromine's got the highest. Because of the oxygen, CH2OH has the higher priority than the CH3, which has just hydrogens. And I'm going to put the same priorities here because the atoms are exactly the same. CH2OH is 2, and then the CH3 is 3. So we're going to do what we did before. 1, 2, 3, we're going to go around clockwise here, so therefore the stereochemistry at this carbon is R. If we go counterclockwise, this is S. We'd previously said these were enantiomers because we could draw them as mirror images, and figuring out that the stereo centers are different just backs that up. Now, let's get on to the concept of we're not talking about just enantiomers, but we're talking about things called diastereomers as well. Simple definition down here. Stereoisomers that are non-superimposable mirror images are known as enantiomers. We talked about that before. Diastereomers are stereoisomers that are not mirror images at all. And you tend to see diastereomers more when there's more than one stereocenter present. So for example, 2,3-dibromobutane. If I was to ask you, how many stereocenters do you see in this molecule? Hopefully what you'd say is, well, there's one here, and I don't know what's going on there, and you'd say there is one here. Oh boy, sorry, I don't know what's happening here. Let me try that again. Bloody thing. Probably made by an Englishman. Anyway, so there's one stereocenter, there is another stereocenter, 2 stereocenters total. Now, I don't know whether you guys know, there is a way to tell how many stereoisomers you're going to be able to draw for a particular number of stereocenters. And that is 2 to the power n, where n is the number of stereocenters. So therefore, in this case, it's 2 to the power 2, which means we're going to be able to draw out 4 stereoisomers. And here's what I'm going to do. I'm going to draw out these 5 carbons, I'm going to draw them out 4 times, because there's going to be 4 stereoisomers. And the chiral carbons are on carbons 2 and 3. And if you remember, when we draw out stereocenters, the thing we're doing differently is we're putting on the wedge and the dash. I'm just going to indicate the wedges here, the wedges and the dashes. All right. I'm just going to indicate the wedges and the dashes for the bromines, not for the hydrogen that's on there as well, because hopefully that's going to help illustrate what we are talking about. So for the first one here, if I know there are going to be 4 stereocenters, then I'm going to draw one where perhaps both the bromines are on wedges. Alright, so that's one possibility. So could you think of any other possibilities of how I can arrange those atoms? Well, one is where I have both bromines not on wedges but on dashes. So in other words, in the first structure both the bromines point up or towards you, in this case both the bromines point away from you. So what do you think the other 2 could be? Well, of course the other 2 are where we have one of each. So first I could have, say, a bromine pointing up, and then on carbon 3 a bromine pointing down. And then what would this last one be? Well, it would just be the opposite of this one, where first I have a bromine pointing down, and then I have one pointing up. Now the reason I'm going through this is, if I label these A, B, and C, and D, is I want you guys to be able to recognize how we can tell when we have a pair of enantiomers and when we have a pair of diastereomers. Okay, so we're going to come up with a bunch of relationships here. We're going to compare A and B, we're going to compare A and C, we're going to compare B and C, we're going to compare B and D. Now I want to make sure that I get all these pairs right. There should be 6 pairs, I think. C and D, and which is the one I'm missing? I'm missing A and D, I think. Alright. Now, take a look at A and B. Can you see two wedges, two dashes? Can you see in each case both or all the stereochemistries are different? You remember earlier on we'd said when all your stereocenters are different, it means you have a pair of enantiomers. In this case you only have one stereocenter, but the principle is still true here. This and this, if you flip this one on its back, you'll see it's the mirror image of this. But if you put this on top of here, they don't match up because the wedges don't match up with the dashes. The stereochemistries at both these carbons are exactly opposite between A and B. Therefore, what that means is that A and B are enantiomers. Okay? So, if A and B are enantiomers, can you see which other pair of molecules are enantiomers? It's the other pair where both stereocenters are exactly opposite to each other. And of course that is C and D, because here we've got down and up, and then we've got down and up, and then we've got up and down, or up, down, down, up. They're exactly opposite to each other. Now, if A and B and C and D are enantiomers, then what about all the other pairs? Well, let's take a look at A and C. Here's A, here's C. Notice how between those two, the carbon 2, the stereochemistry is the same. For carbon 3, the stereochemistry is opposite. So the question is, are both stereocenters opposite between A and C? The answer is no. These cannot be mirror images of each other, because here the stereocenters are both pointing up. I can't make this anyway into these both pointing up. So therefore these are diastereomers. So that is A and C. They're diastereomers. So I'm just going to put enan for enantiomers and dia for diastereomers. Alright? I realized I shouldn't just put D because we've got D down here. So what about B and C? Well, B and C is very similar to A and C. We have one stereocenter that's exactly the same, one that's flipped, therefore these cannot be mirror images of each other, and therefore these are also diastereomers. What about B and D? Well, it looks kind of familiar. One stereocenter is the same, one is opposite, therefore these can't be mirror images either, and these are also diastereomers. And then the last one, A and D. Carbon number 3, the stereochemistry is the same. Carbon number 2, the stereochemistry is opposite. These cannot be mirror images either. So therefore these are also diastereomers. Okay? We said 4 stereoisomers, and that's exactly what we have.